Good morning to those of you that are already in the room. We're just going to wait for all the attendees to join us, and then we'll get started. All right, good morning, everyone. My name is Ben Murphy, and I'm a physical scientist in the Office of Research and Development at EPA. I'm joined by my co-chair this morning, Dr. Havala Pye, also an EPA ORD, and together we welcome you to the final day of the 19th Annual CMAS Conference. I think we all miss being in person together, but I do want to say that I've really enjoyed getting to learn from the presentations and webinars this week. I would even say that there are components to this virtual conference that I think support an even deeper understanding of the work that we're sharing with each other than the traditional format does. And I think that's very much to the credit of all the organizers and support staff in CMAS. So another warm thanks for putting together this opportunity. This morning's plenary session is titled Connecting Real World and Experimental Aerosol Observations with Improved Large-Scale Model Developments. And although it's not mentioned explicitly in the title, we very much want to keep in mind that our motivation behind developing such models of ambient particulate matter is to address the urgent needs societies have for protecting public health and responding to climate change. And I know these concerns will very much be a focus of the talks today. Our two distinguished speakers will address this session's focus from two different perspectives, informed by their current research and expertise. First, Professor Kelley Barsanti will speak to us about the newest results in understanding the chemical composition of wildfire emissions and propose a new tool for curating and disseminating that critical data. Then Professor Joel Schwartz will demonstrate how we can apply multiple atmospheric model datasets together to achieve greater insights into how air pollution management can better protect public health. Following each presentation, we will have some time for targeted questions from you. And then following the Q&A with Professor Schwartz, we will open up the discussion to both speakers who will address your broader questions in an open forum format at that time. Please, as you have learned this week, submit your questions via the Q&A chat interface, and Dr. Pye and I will pose those questions to the speakers, or if we start running low on time, they can address them directly themselves in that interface window. And with that, I'll ask Professor Barsanti. Oh, I'm sorry, could you advance the slide, Havala? I missed the cue. So here are our speakers and the titles of their presentations, which hopefully you have seen already. But as we kind of move on to the next step, I'll ask Professor Barsanti to share her screen while I share some brief biographical details of her career. So Kelley is an associate professor in the Department of Chemical and Environmental Engineering and the Center for Environmental Research and Technology at the University of California, Riverside. Her research interests are in improving the process level understanding and model representation of fine particulate matter in air quality models. Her primary research tools include comprehensive two-dimensional gas chromatography and multi-scale mechanistic models. And her current research projects include improving the speciation of organic compounds in emissions inventories for wildland fires, advancing the model representation of secondary organic PM formation in smoke plumes, and evaluating the effects of COVID-19 shelter-in-place restrictions on air quality in the South Coast Air Basin. She has authored or co-authored over 40 papers on these and related topics. She earned her PhD in environmental science and engineering from the Oregon Health and Science University in Portland, Oregon. And she served as a postdoctoral fellow at the National Center for Atmospheric Research in Boulder, Colorado. I also want to mention of particular interest to some in this community that Kelley served on the most recent CMAQ external peer review panel in 2019, hosted here in RTP, where I am in RTP at least. And there she contributed her breadth of expertise to help guide the future of that model's development, particularly on issues of chemistry and aerosol formation. So on behalf of the CMAS community, I want to thank Dr. Barsanti for sharing her work with us today and hand the floor to her.
Thank you, Ben, for the introduction, and thank you all for the invitation to be here. This is really an exciting opportunity to share the work that we've been doing in wildland fire emissions and thinking about linking these measurements to models. So I always like to start with my acknowledgements because I usually get nervous and forget them at the end. So I've had a wonderful group of PhD students and postdocs that have contributed to this work, as well as collaborators over the years. So starting with Brian Lamb and his group at Washington State and Bob Yokelson, collaborating with Christine Wiedenmeyer when she was at NCAR, and Louisa Emmons and John Orlando, and more recently on some of the field measurements with Alan Goldstein. The measurements that I'll be showing today in the data came from efforts during Flame 4 and FireX. So huge thanks to the lab and field crews there. And been fortunate to have funding from NOAA, NSF, CARB. And again, this all kicked off with the JFSP, some JFSP funding, and recently some support from HARIBA. So to those of us in the Western US, this is very obvious, but the intensity of wildfires is increasing. This 2020 season in California, we had 6 of the top 20 largest wildfires in California history, and many of these were burning concurrently. This is the same in Colorado, where we have the Cameron Peak Fire, which is burning, which is the largest fire, in recorded history, and Pine Gulch Fire, which is also still burning. Actually, Pine Gulch, I think they now have under control, but this is the second largest burning fire. So we also know that in addition to this intensity, right, intensity being the size of these fires and acreage, the frequency and duration are also increasing. And I actually stole this from the recent National Academy Smoke, where someone said, where there is fire, there is smoke, right? And so whether you like the satellite imagery or this just massive reddish purple color in the purple airs, we think about the health, automatically think about the health and climate impacts of these fires. One of the things that I've been thinking a lot about, though, is that when we're thinking about health impacts and when we're thinking about models, I think it's really important to keep in mind that it's more than these mega fires, right? Especially in California, attention is drawn to these fires that are threatening these multi-million-dollar homes, and they're typically put out pretty quickly. I mean, 1 or 2 days, right? And that's because they are, in fact, threatening structures. But we have the case where a lot of these fires just burn and burn for days and weeks and even into months. So if we look at the average days that some fires burned in the early 70s to the early 80s, the average burn time was about 6 days. More recently, we're moving into an average fire burns 52 days, right? And of course, there are land management decisions involved here, right? So we've got to knock down that fuel. But in terms of the health impacts and how we model smoke, I think this is important to keep in mind, right? And we think about not only these acute health effects, but the chronic effects of the smoke exposure. And of course, again, those of us in the Western US, we like to go to our favorite places and we like to be able to see them. So thinking about the visibility implications is important as well. And I spent, this picture on the right is actually near my home. So I spent about 8 weeks in Southern Colorado in May and June, getting support from my family as part of my transition to being a full-time professor and full-time homeschooler. So, and one of this really interesting things happened that I hadn't ever experienced, at least since I started studying wildfires. And that is that every morning about 5 o'clock, I was awoken by this strong smell of smoke coming in my window. And I was talking to Bob Yokelson about this, and he's like, this is what I've been talking about, those nighttime downslope winds, right? And he shared this data set with me from Missoula, Montana. This is just a subset, but you could actually see this very clear pattern for months, where what I'm showing here is PM 2.5 measured in micrograms per cubic meter. And then we have a time scale, and you just see that during basically the nighttime hours, 8 p.m., the concentrations in that valley start rising and they peak at 6 a.m. and then they go back down. So there is like this almost synoptic scale of 6 a.m. peak in smoke emissions in the valley. And I think that this, and I really live this. And so again, it's something to be thinking about as we're thinking about modeling smoke, I think. Okay, so I want to acknowledge, given that this is a modeling group, I want to acknowledge that when we think about the spatial and temporal distribution of fine particulate matter, PM2.5, right, that this is of course driven by both dynamics and chemistry, and my focus is on the chemistry. If we think about a temperate forest, either wildfire or prescribed burn, about 90% of the primary PM2.5 is organic carbon, which is why I have organic carbon shown here. So the particulate matter, organic carbon, if we only thought about dynamics, would decrease, right, due to dilution in time and space. And if we only had secondary chemistry, that OCPM mass would increase in time and space. And what we see in the field, right, is some sort of combination of these two processes where we can have essentially flat mass in time and space, a slight increase or a slight decrease. So in words, right, the chemical conversion of gas phase OC to particle phase OC during plume evolution occurs, right? And this is that secondary OC or secondary organic aerosol formation. This changes the mass concentration and distribution of PM, right? So we may not change the mass concentration much, but we certainly change the distribution of PM, which influences the health and climate effects. And I would argue that this is poorly constrained, right? Our understanding of these processes, especially when we try to link it to like fire dynamics, is not very robust. And it's very challenging to capture this in an air quality model. So, but I'm going to focus on this aspect in this talk, both in terms of measurements and modeling, and again, just focusing on this, largely this chemistry part. So I wanted to just give a couple examples of CMAQ predictions in fire impacted regions. So on the left, this first example comes from a paper led by Kirk Baker, where they were modeling the Rim Fire 2013 in California using CMAQ version 5.2. You have time on the x-axis, and then these are species or constituents ratio to CO. The black dots are the observations. Model resolution 4 kilometer are the red X's, and model resolution 12 kilometer are the blue triangles. And what you see, right, is that there are these, sort of interesting ozone behavior, and modeling ozone and smoke is extremely tricky. You can have formation or depletion events, and you sort of see this potential formation event and the model really doesn't capture this. And then in terms of capturing the OA, the model is really under predicting this OA at the beginning, sort of closer to the plume. And as it looks like, dilution's occurring and maybe some chemistry, but that OA to CO is decreasing. And the model is, in better agreement, but the model is, the ratio of OA to CO is completely flat, which is not exactly what's seen in the observations. I will say, if you look at the bias in PM2.5, organic carbon, it on an average sense, it sort of averages out. So this is compared to 3 STN sites. And as the modeled fire contribution increases, right, so again, that closer to the fire, the bias becomes worse. And this is a plot, this is actually some of the very earliest modeling work that I was involved with and part of that JFSP, where this is air-packed simulations at 4 kilometer resolution using CMAQ version 5.0 of the Pacific Northwest in August of 2015. And the size of the circles are the PM2.5 concentrations, and then the color represents fractional bias. So you see that this version of CMAQ was largely under predicting PM2.5 everywhere in this region during that time. And in both cases, most of the PM2.5 organic carbon or organic aerosol is primary, and measurements show us that that's not likely. Okay, that largely we have much more secondary than is predicted by the model. So at that time, one of the most straightforward approaches, it seemed to me, to getting at better models, better predictions, was to do a better job identifying the pollutant precursors, right? So this is a figure from Karsten Warneke's 2011 paper. And these are mass spectra of 2 different fire types, so maritime chaparral and pine and spruce needles under 2 different combustion conditions, so flaming versus smoldering. And the basic point here is that anywhere you see blue or green, that indicates an unidentified species. Okay, so as we move to these higher molecular weight compounds towards the right of this mass spectra, we can see that there's an increasing fraction of unidentified compounds. And you know, this ends up being about 26 to 53% by mass. Bob Yokelson presented something similar in 2013 where they summed emission factors, and about 30 to 45%, again, across fuel types, that varied by fuel type, of that summed emission factor was unidentified gaseous non-methane organic carbon, so NMOC. Okay, so we said, well, we can just improve predictions by measuring more compounds, right? So we set off to do so. We set off to do so in the Missoula Fire Lab twice, in Blodgett Forest for prescribed burns. We've been there once. We're going back hopefully this fall. We participated in Fire XAQ. We flew on the NOAA Twin Otter, and also were aboard the Aerodyne Mobile Lab. And so some of our earliest results are shown here. And I realize that you can't read these axes, and that's okay. What I want to point out is that in a given fire type like black spruce, we were able to identify 400 compounds, right? So this is a factor of 4 larger than what had been reported and identified before. And we started, because we're interested in chemistry, we started just making these figures where we just group these compounds that we measured by their compound class. So across the x-axis, the bars represent aromatics, oxygenated aromatics, hydrocarbons, terpenoids, oxygenated hydrocarbons, furans, and nitrogen and sulfur containing compounds. And then we also separated them by carbon number, that's the color, and then additional functionality using these different shapes. So what's really clear here, both in this bar chart, is like for black spruce, there's this huge terpenoid component, right, in the emission factor. You can also see that if you're used to looking at chromatograms in the chromatogram. So then just comparing to other fuels, you know, one of the things that jumped out is that the distributions of compounds in these that are being emitted by these different fuels is very, very different. So for this rice straw, we see, for example, a lot of oxygenated aromatics and no terpenoids. And then peat is sort of well known for this strong alkane signature, which is represented by this bar here. And then this, this signature peak distribution in the chromatogram. So we started thinking that this has to influence the chemistry, right? And we specifically started zooming in on the terpenes just because this is something we know is important for SOA formation. So that's where we went next. So we started looking at the terpene distributions as a function of fuel species. So you can see these shrubs have relatively low emission factors, but then there's some interesting things that appear, like there's this relatively large oxygenated monoterpene peak when we burn sagebrush. And then when we start digging into the conifers, we see really big differences in the emission factors, both the total emission factor, and again, so I didn't go through this, but the height of the bars is the emission factor, the grams of compound per kilogram of fuel burned, and the color indicates composition, general classes of composition. So when we burn the canopy, we get huge terpenoid emission factors, and much less so when we're burning composite log, duff, and litter. And this actually got us thinking a lot about prescribed burns, which I'm not going to talk about today, but this was an interesting result. Just the influence of actually the component on the total terpenoid emission factor. Okay, but because we're interested in chemistry, we dug down a little further, and what I've shown here, lodgepole pine in the top. So I like to say, right, if I look at these trees, they look the same to me. I wouldn't know what's coming from what, but it's very cool that they have completely different chemical signatures. So this is a list of the top 10 monoterpenes and their fraction of the emission factor. And the box and whiskers is what we measure in smoke. And what we've overlain here are published essential oil distributions. So what's really cool is we start to see that basically what we're measuring coming off these trees is just distillation of what's being stored in the plant tissues. And we can see that only in a couple cases do we likely actually have like a combustion product. So it's pretty interesting. But then again, in terms of thinking about the chemistry, beta-philandrine is the dominant compound from lodgepole pine, while camphene is one of the more dominant compounds from Douglas fir. And we went in and started doing some lab and modeling studies on camphene, and camphene makes a lot of SOA. So this is why we really care about these details, is we think that it ultimately makes a difference. Okay, so I'm going to summarize in 2 slides what our measurements results have been. And I think the first thing is that we did, in fact, identify a large number of compounds that were not in inventories or speciation profiles. This is just an example of the gaseous non-methane organic carbon emission factors in pine smoke. And we've organized these in terms of volatility. So this is the saturation concentration, the log of the saturation concentration, going from most volatile on the right-hand side to least volatile on the left-hand side. And we actually have the number of compounds in, for example, we said typically measured compounds, and we attributed that to Akagi. That's being generous with typically measured. Akagi had a large number of species. And then we compared that with the EPA speciate as well. So what we see is similar to what Karsten was showing in his paper, that for the most volatile compounds, right, these have been well measured and are sort of well understood. And so our measurements, we have about the same number of compounds. We measured the same number of compounds that are commonly reported. But as we move to lower and lower volatility species, and maybe arguably these might be stronger SOA precursors, right? The number of compounds as well as the total emission factor is significantly decreasing in the inventories. So these compounds are not being represented in models for the most part. The second thing we did is we found a lot of gaps in the data, right? So this is going to really lead into the second part of my talk. And what we wanted to do is we said, okay, we've measured all these things. Now let's put them in a model. Well, what we started seeing is, do we even know anything about the SOA formation from these compounds that we're looking at? So we took and we titled this reactive carbon. So what we did is we took the top 100 compounds by emission factor, which is about 90% of the total non-methane organic carbon. And we scaled that by OH reactivity and carbon number, right? And I know that reacting with OH is not the only thing that forms SOA. And I also know that, isoprene tells us that carbon number isn't all that matters either. But just as a way, I said, okay, if you could tell John Seinfeld, right, what to put in his chamber, right, you want to make a targeted list. So we started thinking about that. So the pie charts, what we've done here is if we take all of those compounds, we just took a pie chart and said, for all of these 100 compounds, how many publications are there about SOA formation? And less than 20% were well studied, which had 5 or more publications. And what you see is that really, 50 to 75% were understudied. And a lot of these compounds had 0 to 1 publications. So what we did then is we said, okay, based on this sort of reactive carbon, we listed the top 10 compounds that were understudied for each fuel type. And so one of the things that jumps out, there are a lot of furan and furan derivatives here. Again, camphene is popping up in a number of the fuel types. So we've done some follow-up work where we developed a SAPRAC mechanism for furans, and that's been recently published in ACS Earth and Space Chemistry. And we have a paper under review modeling camphene SOA as well. So the idea here is that we cannot improve predictions only by measuring more compounds, right? So we did identify compounds that may be important. We characterize compounds as a function of fuel species, component, and combustion efficiency to some extent. We've compared emission factors calculated in the lab, in the field, and including as a function of OC mass loading. I'm really not going to talk about those 2 anymore. But what also happened is we just brought up a whole host of questions. It's like can of worms, right? So do explicit and reduced or reduced gas phase chemical mechanisms even exist for the compounds we're measuring? Do SOA model parameters exist for the compounds that might be precursors? Can we represent the gas phase chemistry using existing model compounds? Can SOA formation be represented using existing model parameters, right? So it wasn't so simple as just measuring things. So I want to give some credit to Serena Chung for this slide. I adapted it. She presented it a little while ago and I really liked it. But moving from the measurements to the modeling, right? So there are a lot of factors that go into just generating the total non-methane organic carbon or total PM 2.5 from a fire. And we are just not even going there. This is part of the world that I am connected to in other projects, but this is something that we really won't talk about. I have looked into a little bit how the partitioning between this gas and particle phase changes as a function of various factors, but we're not going there today. Okay, so I'm watching the time, doing okay, but we've been really focusing on these two parts here. So I'm just going to say basically how this total non-methane organic carbon, right? We measured a bunch of individual compounds here, and now we're thinking about how they map to chemical species in a model. And as I mentioned previously, how they're represented in the chemistry, right? In a SAPRAC mechanism, in an organic aerosol model. So a couple of the early modeling results. So what we did is we took the default fin emission factors. They're mapped to Mozart surrogates here. And then we took our measurements, we took 50% ponderosa pine and 50% black spruce to represent temperate forest. And what you see, no surprise, is that the mole fraction, I popped out these compounds that are potential SOA precursors. The mole fraction of those compounds increases because that's what we're better at measuring. And on a mass basis, we get a much, much greater mass fraction of potential SOA precursors. So without even thinking about chemistry, without thinking about adding model species, there's a fundamental shift in the distribution of model species. Moving a little bit away from SOA for a minute, the other thing we did is we mapped the properties of the compounds that were being mapped into a single model surrogate. So I think especially the Henry's law constant is striking. We're not the first to do something like this, but you just see there's orders of magnitude distribution. The aromatics are a good example. We've got from about 10 to the negative, or 10 to the 2, 10 to the up to 10 to the 5th in the Henry's law constant. So orders of magnitude, the differences of all of these compounds. So what we're seeing is we're lumping an increasing number of compounds into very few surrogates, which may influence many processes. Okay, so as you can see, we've kind of opened this can of worms, and honestly, it's a little bit overwhelming. So we wanted to create a shared repository of these emission factors that are easy to update. They include detailed speciation from all of these recent lab and field studies. They can be both sort of condensed, they can be expanded, you don't lose data, allows user flexibility, and links compound, EFs, and chemical and physical properties and model surrogates. So I'm actually, some details of that database are here. It's NEIVA, we're calling it the Next Emissions Inventory Expansion of Akagi. And I just want to go through this real quick, and then I have one summary slide. So the layers of our database are as follows. So typically, most of what's included in an emission inventory is what's on the very right. So you have the compound, you have the emission factor by fuel type, the burn characteristics, and something about the publication details. But what we've done is we've created these layers that are linked by compound ID. And we include compound properties, molecular formula, exact mass, retention times, some primary and secondary chemical classification, a whole list of compound properties, and then I think most importantly, the model surrogates for those compounds. So it includes their SAPRAC and Mozart species. So from a modeling perspective, having these layers linked is extremely useful, and it provides a lot of user flexibility, and I think may be able to get us somewhere. Okay, so I am going to just go ahead and put these up. I think I'm maybe 1 minute over, but basically the advanced analytical instrumentations and these analysis methods are really facilitating a more complete identification and quantification of gaseous non-methane organic carbons, but they're highlighting data gaps. We have a huge opportunity here to rethink the approaches for including these newly measured compounds in current and future model frameworks. And I would just say there's a lot of uncertainty and complexity in modeling smoke. And I think developing these community-based tools can facilitate faster discovery and adaptation, right? Getting more hands on deck. And of course, just as a reminder, and Ben said this at the beginning, that the goal is always to improve predictions. So with that, I'm done. Thank you. I apologize for going a little bit over.
Thank you so much, Kelley. That was great. And we are right on time. So we have about 9 or 10 minutes for questions from the audience. So I encourage all of the attendees to submit your questions through the Q&A chat, of course. And while we're waiting for some questions to pop in, I'll take my prerogative as moderator to ask a couple to get started. I think the first one I'll start with, just because it overwhelms my curiosity, is a point that you alluded to back on the slide that you adapted from Serena, I think.
Mm-hmm.
And you mentioned that you had been doing some thinking about how we distinguish between, I think you put it as NMOC and PM25, maybe?
Yeah, that's right.
Yeah,
Right,
PM25
right there.
and NMOC.
Yeah.
I was wondering if you could just offer us a few more kind of meaty details about what you're considering and what kind of impacts you think it has on our predictions.
Okay, so, you know, what happened here is that we took and we made a volatility distribution from our lab measurements. And we were missing this whole range of compounds, right? And, you know, as a longtime student of partitioning, I shouldn't have been surprised, but I was surprised at first. And then I started doing some calculations and I realized that basically, right, the mass loading in those fire lab studies is so high that that volatility range that we weren't measuring in the gas phase was simply because it was largely partitioned to the particles. But I was then thinking about the fact that in the field where we're measuring, often sort of studying smoke, the smoke is actually the organic or aerosol or the PM2.5 is usually 1 to 2 orders of magnitude lower. So unless you're really in the thick smoke, we're significantly lower. So I started thinking that we're probably really underestimating the emission factors for the semi-volatile and intermediate and even I think it's most surprising for intermediate volatility compounds, right? Because we think of those as being in the gas phase, but not when you have 10,000 micrograms of particulate matter. And so we wrote a little bit about this in a paper on ACP that I didn't have here, but we showed the difference in the fraction of the species that would be in the gas phase sort of in the lab versus the field, and how you could completely miss some of these compounds if you're in the field or in the lab, excuse me. And we don't adjust for that at all. Everyone's really focused on MCE. And honestly, I think this is a much bigger issue personally, but that's because it's my lens. Partitioning is the lens through which I see the world.
I can relate to that. Yeah, thank you so much. So we have a question from the audience, and they're asking, what is the uncertainty percentage in your estimations?
Yeah, so Poonam, thank you for the question. So we've published several papers on this, and basically in all of our measurements, we report the uncertainty ranges. I don't have them here. We average, you know, sometimes we have like 70 measurements. And so we start to see really statistical robustness. Honestly, this first paper, the Flame 4 paper, we didn't have very many samples. And we've been conservative. So because we don't have many samples, we assume some sort of maximum uncertainty limits. We've been shrinking those error bars all the time. So I don't have the numbers right in front of me, but we have background subtraction, and we typically say it's something like 2 times the lowest measured compounds, but we've been very conservative. I tend to hire very careful analytical chemists, because if we're trying to say give this community tool, we don't want to be wrong.
I think we'll start. So we have a couple more questions on the Q&A chat, and I think we'll start with the short one first, and then we'll go to the longer one. So first, Cara Scalpone says, thank you for the excellent presentation. You mentioned updating the Fin model with new emission factors that reflect your observations. Has your lab done any photochemical model performance evaluation using the emission inventory with your emission factors?
So Kara, not enough. And that's one of the reasons we kind of stopped and started working on the emission inventory. I will say in our JFSP final report, we do present some air pact results where we did update the inventory and we do see a difference. Unfortunately, at the same time, the air pact went from version 5.0 of CMAQ to 5.2. So there's a lot of changes. It was hard to evaluate only the influence of the additional speciation. So we've done a lot in box models, but box models are tricky. We see huge differences, but I'm not sure how real they are. So I would say not enough, and that's why we're really interested in getting this into the hands of more modelers.
Terrific. Tesh Rao has a lengthy comment here. I'm going to go ahead and click the answer live button so that others in the audience can see it and you can see it as well.
Okay.
And if there are points there that you'd like to address, I think that'd be great. I think in the interest of time though, let's, maybe we can address Havala's question. And Havala, if you want to unmute and ask it yourself, maybe that would be a good way to go.
Sure. So I noticed that you mentioned some publications where you've modified chemistry in SAPRAC and Gecko. And I think of those as different ends of the spectrum in terms of like how much judgment and manual information has to be input versus like an automated set of SARs. I was wondering if you could comment on the advantages or disadvantages of those two approaches for including new chemistry.
Yeah, so actually, interestingly enough, the SAPRAC has a mechanism generation tool that I really didn't know existed, but Bill, has these tools in his toolbox and in his brain that, are like not that well known. So the mechanism generation tool actually works very similarly to Gecko. So what we did is we used the SAPRAC mechanism generations tool, but we compared heavily to publications, largely computational chemistry publications, because they're a little bit more systematic. And then we adjusted factors in Nextgen to produce a SAPRAC mechanism. So they're not as different in that respect as you might imagine. But with Gecko, we sort of free ran Gecko, right? And then we compared, so these were, as you said, they're very different approaches here. So with SAPRAC, again, we started with the mechanism generation tool, actually, and we compared to MCM, and then we also just, modified the mechanism based on published data. And then we compared with chamber studies. We did not do any tweaking of the mechanism. In Gecko, we free ran and then compared to existing chamber studies. And I think that comparison is really challenging because there's obvious model measurement differences, but it's pretty interesting. And I just think that the best thing we can do, I think we're sometimes afraid to trust these models that are built on these SARs, but I think what we have to do is sort of push them and compare them to measurements. And sometimes it just indicates where more measurements are needed, right? They're all subject to the underlying data set, right? They can only be as good as the underlying data. So I think we have to just keep pushing them and keep figuring out where the data gaps are.
Excellent. So we're right at the time where we should be switching over. I do want to push our time limit just a little bit and address perhaps two questions. So your co-panelist, Professor Schwartz, has asked if these new emissions have been fed into GFED emissions. And I think I would like to, it looks like there's a short answer to that one.
Nope.
I would like to kind of tie that to Tesh's comment and maybe see if you have some comments for this idea of how we're thinking about scaling up the data that you're collecting to these kind of larger scale inventories where a lot of the development has been focused on kind of higher level issues and trying to describe either regional variation between fuel types or trying to get a handle on the bigger picture of wildfire emissions across large domains of continents and
So this is something that we've been looking at a lot, and one of the things this is one of the reasons I really wanted to start getting in the field, because and I'll share a paper with you, but we basically tried to see we've measured so many things in the lab, but then what happened when we went to Blodgett, if you look at these pie charts of what's burned, you know, every single pie chart's different. I mean, the forest is so heterogeneous, and then we measured like 3 of the species that are actually burning, right? So we're trying to sort of see how we can average the emission profiles that we have to better represent either sort of larger, you know, like mapping to FCCS fuel classifications, for example, but even as you say, you know, what is it okay to just have a wildfire type and a prescribed fire type, and it might be fine, right? So that's sort of what's next. We're sort of how far can we zoom out? And I think it's a good question. And this is again why we wanted to do this. We understand that we can't map at 1 kilometer resolution to the fuel type all the time.
Yeah, unfortunately.
Yeah, I know. Well, I get excited when I see those maps. I'm like, oh, we can link to the 1 kilometer resolution.
Makes one feel, yeah, feel hopeful.
Yeah.
All right, so great. Thank you so much, Kelley. I know if we were all in person, there would be an additional round of applause. I'll hand things over to my co-chair, Havala Pye, to introduce our next speaker. Havala.
Thanks. I'll introduce Joel as he's pulling up his slides. So Joel Schwartz is a professor in the Departments of Environmental Health and Epidemiology at Harvard School of Public Health, on the steering committee of the Harvard University Center for the Environment, and director of the Harvard Center for Risk Analysis. His major research interests include health effects of air pollution, heavy metals, climate change, and drinking water, as well as epidemiological methods, risk assessment, and cost-benefit analysis. He has examined these questions using a variety of methods, including time series, case crossover, and case-only analyses of administrative data, survival, and repeated measures analysis of cohorts. He's particularly interested in quasi-experimental designs and other causal models to investigate a range of outcomes, including cognitive function, lung function, asthma, and heart attacks, and others. He's also interested in social and other factors conveying increased susceptibility. Recently, he's been involved in exposure modeling using machine learning to combine land use data, remote sensing data, and chemical transport models. Dr. Schwartz's benefit cost analysis on lead and gasoline was critical for its elimination in the United States, and his methods for valuing the benefits of reducing toxins that have cognitive effects is widely used. He's the recipient of a John D. and Catherine T. MacArthur Fellowship and the John Goldsmith Award from the International Society for Environmental Epidemiology. And without further ado, I'll turn it over to Joel. You're muted there, Joel.
Am I unmuted?
That's good. Yes, we can hear you.
Sorry. So I want to begin by talking about exposure models, of which CMAQ is certainly one, and comparing them first to monitoring data. So obviously, if we could measure people's exposure to air pollutants, we would have more accurate estimates of their exposure. But typically, you know, we have 1,000 to 2,000 monitors in North America, depending on the pollutant that you're looking at. And for some pollutants, it's fewer than 1,000. And North America is pretty big. So clearly, a lot of people live too far away from those monitors. And so that creates problems for us, which is why modeling is important. Those models help us do a number of things. They can identify hotspots where we're not monitoring, so we don't know that that's a hotspot, but the model can help tell us, you know, there's something going on over here. They're good for estimating exposures for health studies. And the alternative, which is personal exposure measurements, is still too expensive to use for large numbers of people. You know, there are 121,700 participants in the nurses' health study, and you're not going to get all of them a purple air, nor are they going to carry that purple air with them for the rest of their life. So we need different ways of assigning exposure to people who are in health studies and to the population at large for doing risk assessments. Okay, so chemical transport models is obviously what most of this conference is about. And they are wondrous beasts, and they incorporate better and better chemistry over time and better emissions inventories, as we've just heard about. And they have a high temporal resolution. In general, they only have a modest spatial resolution for health studies. I mean, you know, I know some people in England who are running CMAQ on a 30-meter grid in London, but, you know, that's kind of unusual. And we generally don't have emissions inventories that would support that. So more typically, we have 12-kilometer emissions, 12-kilometer grid cells that estimates are produced for, and that's not so great in terms of assigning exposure to people. So problems with the models are, besides the limited spatial resolution, is they're based on emissions inventories, and as we've just heard, they're not perfect. And so, you know, if you put in, you know, incorrect emissions, it's not surprising that your models are going to produce somewhat erroneous predictions. Even the reanalysis weather data that's going into the models has some errors associated with it. And one of the issues, particularly with emissions inventories, is many of them have limited temporal variations. We actually really only know the annual emissions from a lot of sources. And then we have some models, which again, have errors associated with them to try to spread those out over the course of the year. And so all of those things contribute to errors. We have incomplete chemistry. On the other hand, these models are absolutely necessary for what-if scenarios. You know, if EPA wants to know what are the benefits of the cross-state air pollution rule, they can run the model with and without changes in emissions that rule would produce, and they can get estimates of what the impact will be. And there's really no other way to do that. Because of these other issues, however, the R squared, you know, the percent of total variation explained at monitoring locations for these models is modest. And we'd like to have it be better, particularly for health studies and risk assessments. So a common approach used in health studies are things called land use regressions. And they basically take land use patterns, which are primarily surrogates for emissions. So, you know, traffic density is clearly a surrogate for emissions. A lot of green space is a surrogate for not so many primary emissions, but maybe more VOCs, right? And then they fit models, statistical models that calibrate that to monitoring. Typically, that monitoring, because again, we don't have, you know, we have under 2,000 PM 2.5 monitors in the United States. That's not enough. They'll put out, say, in an urban area, a bunch of additional monitors, but they can't afford to do that for long. So, you know, it's a one-year campaign, or even, you know, 1 month in each of 4 seasons, and they fit the model. And the problem is that, remember, we're using these land use terms as surrogates for sources and sinks for pollutants, and that surrogacy could change. You know, the same number of cars per day outside your house in 2000 resulted in more air pollution than it does now, because we've gradually been getting rid of older, more polluting cars and buying new cars that have better catalytic converters, etc. So this surrogacy changes over time. And so the temporal resolution of these models, first of all, they usually predict annual averages, and a couple of years down the road, they may not be so good if new pollution controls have changed that surrogacy relationship. Now, another set of models are based on satellite remote sensing. So for example, MAQ AOD gives us aerosol optical depth on a 1 kilometer grid for the world, right? And so we actually have measurements in lots of places where there are no monitors. So that's wonderful. And in principle every day, except for the fact that 3/4 of them are missing because of cloud cover, right? So that's a problem. And the other problem with the satellite remote sensing, and this holds for the NO2 and ozone monitoring as well, is that they're looking at column measurements. And the relationship between ground level and the total in the column fluctuates over time. And so we need ways to calibrate that. And people have done a lot of things, including me, to try to calibrate these models and gotten pretty good results. But again, there's room for improvement there as well. So hybrid models are things that try to combine all of these different inputs to get the best of all the different worlds. And that's what I want to talk about today. And so in using these hybrid models, we take a lot of different predictor variables. So we have meteorological variables. Now, obviously, that data goes into the chemical transport models as well, but to the extent that those models have produced some error, right? And we have other variables that might be able to capture some of that error, using them in the hybrid model makes sense. And of course, for trying to relate aerosol optical depth to particle concentrations, the height of the planetary boundary layer is clearly important, as well as wind speed and direction. Then we have land use terms, as I've mentioned. So we have urbanization, we have traffic density, we have data from the Highway Administration on truck routes, the number of trucks on each road segment, the tonnage of truck volume on road segments, etc. We have green space, elevation data, impermeable surface. We know the density of workers by census tract. We have restaurant density data, point data on that, etc. Then we have the satellite remote sensing data. So I mentioned the MAQ AOD. We also have land surface temperature. We have data on soil moisture. We have the absorbing aerosol index, NO2 and ozone from OMI. We have light at night data, which is a pretty good surrogate for traffic intensity, etc. And then in the models that I've been involved with, and others have been fitting, the typical chemical transport models used are CMAQ and geoschem, sometimes WRF chem, and then these sort of fusion products that include chemical transport models like MERA2 and ERA5 from Copernicus. And all those data are available, and what we want to do is we want to calibrate that to monitoring data to get the best possible predictions that we can. Now, unlike CMAQ, which does what ifs, we're predicting the past, right? I don't have satellite remote sensing data for next year, right? That's not going to work. So this is predicting what happened in the past so that we can use that to do risk assessments, health assessments, etc. So that's certainly a key limitation. So we want to put these data together in some intelligent fashion, calibrate it with the monitoring data that allows us to predict PM 2.5 and particle components everywhere. So the approach that we've used, and that's become the most common in the last few years, is machine learning. Now, machine learning is basically statistical modeling, right? Nice thing about statistical modeling is you do get confidence intervals. So that's nice, but it evolved not from statistics, it evolved out of engineering and physics to some extent, and it was related to people wanting to develop programs that could learn to predict things. So they wanted to classify or estimate something, and they wanted a generalized algorithm, right? You train a machine to do something, you want it to be able to deal with scenarios that are not identical to the one that you trained it on. And similarly for me, if I train my model using monitoring data, I already know what the exposure is near the monitor, right? I want to use this to predict what's happening away from the monitors. And so we need to have some way to do that, and therefore predict generalized prediction. And the usual way to do that is to divide the monitors into a training set and then a held out bunch of monitors that aren't used and therefore can represent what's happening at places that weren't used to train the model, and you can evaluate the model on this testing set. There are, Avogadro's number of machine learning models by now, and there's actually a general theorem that is actually less than a decade old, that shows that by averaging predictions from different models, you can do a little bit better than by choosing the best single model in general. And so that's typically what people do. And of course, there are simpler and fancier ways of averaging. So people who don't know it, let me give you a quick introduction to machine learning, okay? So I'm going to talk about a tree model, and a tree model does the following thing. I have information on the left about people's age, occupation, gender, etc. The question I want to answer is, does the person like to play computer games? And what a tree model does is it looks at all the variables you have, all the predictors, and it finds one predictor such that if you split it at a particular place, that does the best job of classifying people into liking computer games and not liking computer games of any single variable and at any cut point for that particular variable. So there is no other split better than age less than or greater than 15 in this toy example for making that judgment. And then the tree goes on and says, well, let's have another branch. Okay, if I were to only split on one additional variable, which could be the same one, what is the best split that I could make? And in this example, the answer is males versus females. So that is a tree. Tree models have been around for a long time, and that's not machine learning. Machine learning models are a forest of trees. So the way a random forest model, which is a machine learner, works is, so you have that first tree, which we spoke about over on the left. And then what we do is we sample from the data with replacement. So I draw a sample that's the same size as the original sample, but every time I select one observation out of it, I keep it here, but then I put it back. So what happens is I'm artificially generating some noise in my data set because some of the people will wind up in my new data set more than once, and some won't be in there at all. So that permutes things a little bit. And then I also take a sample of the variables that I'm going to use for my classification. And using that, I have another tree. And in that tree, the best split is on whether or not they use computers daily. And that's the second tree. And you do this typically hundreds of times. And that means two closely related predictors. If one does a little bit better job, it doesn't always win out because in some of these samples, it's not there. And the other variable gets to do the predicting, okay? And that turns out to produce much more generalizable results because the fact that this variable is a little bit better predictor than the other one, it is often a random factor about the nature of your sample. So we fit trees with a bunch of branches. We take a bunch of these samples and we average them. That's a random forest. So that's an example of machine learning. So for example, in a paper we fit to model PM 2.5 on a 1 kilometer grid for the United States. So that contiguous United States, about 11.5 million grid cells daily from 2000 to 2017. We use 3 machine learning algorithms, neural networks, random forests that I described, another called gradient boosting. And then from what I was saying, you can tell that how many branches, how many different trees I grow, and what fraction of the variables I take subsets of are clearly parameters that can be adjusted, and you adjust them to do the best job on the held out monitors. And then we combined them in a model which allowed more weight to be given to one of these algorithms than another in different parts of the country, so the weights could vary spatially, and the weights could also vary with the PM 2.5 concentrations. One might do a better job at high PM levels than another, but they might do equally well, or it could do worse at low levels. So, so this is sort of a diagram showing, how that basically works. We have a discrete air pollution model. We put it into 3 different learners, and we combine them together, and we get this prediction. That's the map down on the bottom, which I want to thank Jim Kelley for producing that. I mean, from our data, but that's his map. So, whoops. So we got an R squared of 8.89, 89% of the total variation, right? So that's like a correlation coefficient of like 0.95. That's really pretty good for the annual averages. It was a little worse, but not much for day-to-day variations. And these are the predicted power at the held out monitoring sites. And the relationship between predicted and measured was linear. What's interesting is that different algorithms picked up different predictors as being important. So here you can see on the left, gradient boosting, CMAQ PM 2.5, but also the sulfate levels and the elemental and organic carbons, but also MERA2 sulfate levels and OMI NO2 measurements were in the top predictors. For the neural network, the AOD variables were more important. Road density, land cover type things are important in all of these. And our model, which is the one on the right, if you compare to the EPA's Bayesian downscaled CMAQ model, you can see that ours is blotchier. It's not as smooth. It's picking up more fine scale variation than the other models. And that's what we were hoping for by putting in all these fine scale land use terms. And here are blowups in the New York metropolitan area and in California. You can see, as usual, the Central Valley, has high particle levels, but you can also see that we're picking up variations that are far away from the monitoring sites in the valley. And so we're learning about things on fairly fine spatial scales that we can't tell just by looking at the monitors or by 12-kilometer grids. And we even have a nested model that looks at variations within the 1-kilometer grid cells we have. And if we ran that on a 100-meter nested grid, this is what we're getting in Boston. So how does that help our goals? Well, it gives us exposure everywhere, etc. So here's an example of an epidemiology paper using this exposure model, where we looked at long-term and short-term exposure to PM 2.5, ozone, and NO2, truncating the data, throwing out all the people whose observations were greater than 12, greater than 11, greater than 10, greater than 9. And you can see that the decision not to tighten the PM 2.5 standard from 12 is completely unjustified based on the health data. We also see that there are health effects of long-term ozone exposure, and we don't have a long-term ozone standard at all. We also modeled uncertainty here. That's important, to know how well you're doing. Besides an overall level of 89% R squared, we're not doing the same everywhere in the country. And we want to have measures of that, which we can incorporate into our epidemiology. And so here is a model of the uncertainty in the predictions. And you can see that we do not do well in the mountains. Well, that's not surprising. The input variables we have, AOD doesn't do as well in the mountains. CMAQ doesn't do as well in the mountains. And so we don't do as well in the mountains. Other than that, we do pretty well in the US, up in northern Maine, where there are no monitors for us to calibrate against. Again, we have more uncertainty. So let me go on because I'm running out of time. So we can do spatially resolved risk assessments. So there's a gridded population. So you can get the population in the United States on one kilometer grid or even 100-meter grid. And so we combine that with our 1 kilometer grid cells for predicting PM 2.5. So we have the population, we have the 1 kilometer grid cells, and then we were able to get mortality data on a zip code level. And so we assign that to the grid cells that were contained in every zip code. So we have baseline mortality rates on a fine scale. And so we can estimate, if we reduced PM 2.5 in Chicago by 40%, how many fewer deaths would we get by grid cell? And so you can see up here on the North Shore of Chicago, that's where we're getting 2 to 3 fewer deaths per year in each of these grid cells, and then more wide space where it's 1 to 2, and then the gray cells are fewer than 1 life saved per year. And so you can see where the burden of PM 2.5 exposure is distributed geographically in Chicago. So you can do really fine scale risk assessments, and the city can use that to say, well, where are we going to target some interventions? This is the same thing in Houston. And you can see that the western side of the city is where we're getting the largest number of deaths associated to not reducing particles by 40%. That is primarily because here's the average PM 2.5 from our model from 2013 to 2015, and you can see that the highest concentrations are in the western part of the city, but not entirely. We have spots over there. But the green dots are the monitors, and they don't have any monitors over here on the western side. So we showed this to the city of Houston, and the Air Quality Monitoring Board agreed that they were going to move a monitor over into the western side to check that this was true. And if so, then they would know that, oh, well, here are some hot spots, and we need to think about what to do about that. Because they were mostly monitoring by the ship canal, which is important for ozone, but not as important for PM 2.5. So, so we were able to do things like that as well. We've also been fitting models for particle components. This is showing you, for example, OC and nitrate models in the Northeast. And we're now looking at even more machine learners and more particle components. So this is, you know, from a preliminary model we've been fitting, looking at all these different learners and then the ensemble of them for predicting bromine concentrations. And here, of course, we have fewer places to calibrate because we don't have as many speciation monitors. But we're doing a reasonable job with bromine. And so we're going to be doing all of the standard particle species nationwide as part of this model. And we hope to have the annual averages done by the end of the year for 2000 to 2018. So I am over time and I apologize, so I will stop there.
Thank you. We do have maybe about 7 or 8 minutes where we can do questions for Joel, and then we'll open it up to broader discussion for both panelists. There are a number of questions currently in the QA box for Dr. Schwartz. So the first one is from Shiying Chang. Dr. Schwartz, could you comment on the difference between using the black box machine learning algorithms like neural network versus the traditional statistical models like regression models?
Sure. I started off using the traditional statistical models. They're not nearly as good. You know, the machine learners, you know, if you go back to my toy example for regression trees, you know, first we split on age and then on gender. So that effectively is capturing a multiplicative interaction between age and gender, right? That's built in. Also, if I ran the tree lower, it could split on age again and again, but instead of splitting on even intervals of age, it could split on finer intervals in places where the age dependence was nonlinear and broader intervals where it was linear. And so the advantage of machine learners is they incorporate nonlinearities and interactions as appropriate to make good predictions. Now, generalized additive models will incorporate nonlinearities, but you get really limited in terms of looking at interactions between nonlinear predictor variables in a generalized additive model. It starts to become, you know, you run into something called the cursor dimensionality. So they're just better.
Thank you. We have another question from Carl Seltzer. Are there any studies that highlight the importance of such high resolution, for example, 1 kilometer exposure predictions when performing an epidemiological analysis? For example, is there a study that shows considerable differences between, for example, a 4 and 1 kilometer exposure with all other variables held constant? And with that said, how do application of these fine exposure predictions for epidemiological studies reconcile the fact that most people don't live within a 1 kilometer area?
Okay, so so I don't have a 4 kilometer model, so I can't do the epidemiology study both ways to compare it. The
I moved it to the answered.
I'm sorry.
If
Oh,
you're
you
looking
do a
for the
different
question, I moved it to the answered so that the audience could see it. Sorry.
Okay, so I can't see it anymore. So I'm missing a little bit about what I'm supposed to respond to. We think, yeah, people. I'm not sure about the second point, whether you mean that people move outside of their 1 kilometer box that surrounds their home. Assuming that's what you mean, yes, that's true. But people spend about half the day, more now, of course, but about half the day at home because they sleep, they eat, various things like that. A, and B, the air exchange rate in people's homes is generally considerably higher than the air exchange rate in office buildings or shopping malls or other places that people spend, so that the importance of the outdoor air quality on the air that they're actually breathing at home is more important for the area around where they live. However, people are collecting data on time activity patterns for people in some cohort studies, and you can use that. I mean, if we know where they work, right, we can put that take the 1 kilometer grid cell that contains that address, right, and then you can take weighted averages of the exposure. So we have the whole country. So to the extent that people collect data on time spent in different locations, we can improve the exposure assessment. Compared 1 kilometer to 4 kilometer, I think the best way to answer that is that if you look at exposure to traffic-related particles, that'll vary in 100 meters. If you live on a busy road versus on the side street, I mean, you look at avenues in New York versus streets in Manhattan, right? There's more traffic-related pollution on the avenues than on the streets because there's more traffic on the avenues than the streets. Now, of course, that's only one source of particles. The sulfate concentrations are going to be pretty uniform across Manhattan, right? But we do get some fine scale variation, and so that's why I think the 1 kilometer is better. But I haven't been able to do the test with that. So yes, so an important finding, at least for us, is that different machine learners chose to put more reliance on different predictors. So machine learning is an approach to try to come up with a good generalizable predictive model. It is not an approach to try to do hypothesis testing of what are the most important predictors, because different machine learners will give you different answers because they fit it slightly different ways. So that's a limitation if I want to know where are my what's the most important source of particles in Houston, right? For example, but if I just want to do the risk assessment and the epidemiology, then it's a better approach than alternatives. But certainly we do see different weights given to different predictors in different algorithms.
So how about we try to do 2 more quick questions? So I think you covered this follow-up question from Shengyoung Chang. From David Leiter, what do you think the best way to account for autocorrelation in the monitoring data?
Well, the monitoring data is certainly autocorrelated, but that's true, right? I mean, it's true that, you know, yesterday's air pollution is a pretty good predictor of today's air pollution, right? So what we want is a model that does a good job of predicting that truth, but hopefully a good job of recognizing that when a weather front moves through town, right, that breaks that autocorrelation. And that's why you want to have meteorological variables that either directly or indirectly through CMAQ that are in there to try to capture those phenomena. If you're asking the question of whether the, you know, the confidence intervals for individual predictors are biased, which is an issue with a regression model. Again, I don't care what the confidence interval is for, you know, impervious surface as a predictor of PM 2.5. That's just not what we're trying to do. We're trying to just get an overall higher R squared. And then
We can do the next one real quick from Dr. Shuguo Zhang. He says, thanks for the informative talk. My question is, to what extent do the initial conditions and boundary conditions impact the uncertainty of chemical transport models such as CMAQ? And how do you overcome overfitting problems when applying the machine learning models?
So let me take the second one first. Okay, that is why we hold out monitors, because all of these models will tend to overfit, right? So there's 2 levels of trying to control the overfitting. One is, let's say I have 70% of the monitors for training and 30% held out for testing. Among the 70%, we do cross-validation, where we hold out 10% or 20% of those monitors, fit the model to the rest, and do this internal cross-validation and use that to choose the parameters. And then we do the testing, a second set of testing on the real held out 30%. You know, and if we're overfitting, we don't do as well on the held out monitors. And so that's, so the R squared on the held out monitors will increase and then start decreasing as you're fitting better, and then start decreasing as you're overfitting. That's how you control overfitting. I am probably not the person at this meeting to ask about the importance of boundary conditions in CMAQ. I believe that for the CMAQ runs that I had, the boundary conditions were from GeoChem globally. And does that introduce uncertainty? I'm sure it does. And that's why it's not a perfect model in terms of predicting concentrations, and why we want to, you know, combine it with these other sources of information to come up with a better model.
Thanks. We still do have some questions for Dr. Schwartz in the Q&A, but I think we're going to turn it back over to Ben to have some discussion across both speakers.
Trying to unmute myself there. Thank you so much, Havala. Okay, so yeah, at this point, we want to open up the discussion. So anyone in the audience, please submit your questions, and kind of the general topic of our plenary session today, connecting real world and experimental aerosol observations with improved large scale model developments. And our speakers will address your questions. And I think I will go ahead and seed discussion with a question that Havala and I kind of iterated on. I'll choose this one considering the emphasis that both of you presented in terms of air pollution and public health. So there are areas, California being a good example, that are emphasizing air quality at the community level in addition to regional scale monitoring. So what do you see as the role of personal and home-based monitors or drones and other citizen science data sources in the future of air quality management and policy and regulation as well, if you want to speak to that. And I guess let's start with Kelley first.
Yeah, so I think that the proliferation of these low-cost monitoring tools is pretty exciting. I do think that it's illustrating probably some known challenges with trying to understand exposure and health using regionally cited regulatory monitors, right? On the other hand, I think it's clear there are strong limitations, right, with the tools that are available. And so I like the idea of I like these tools for informing the public in some ways, right? Putting some science, like the citizen science is exciting, right? You have some tools in your own hands, you get to sort of understand what you're being exposed to, but I think it's really qualitative. I mean, the purple air picks up smoke in terms of like the waves of smoke crossing the state, but I think we can't rely on, you can't rely on like the values, right? And then I've seen also, I'll just add one more thing. I'm sure Joel has a lot to say about this, but in my own experience, where we've used these sort of in an educational sense, people will buy these monitors, or we're involved in some of these ARB 617 projects, which is like state money to provide the tools to local communities. And, they want to use like a purple air to measure like traffic pollutants, right? And that the particle size is too small. It's not seen by the purple air. So making sure sort of, I guess the guidance is going to be really needing as these become more and more popular, just guidance on what they're good for and what they're not so good for. And it's out there. Some of that guidance is out there, but some thoughts.
Great, thank you. Dr. Schwartz?
I think Kelley is right. I mean, these can be useful educational tools, and they can be useful for finding out perhaps that a neighborhood unexpectedly has, some high levels, or on a street or things like that. But, the correlation between purple airs and real monitors is not very good. And so I wouldn't use them for epidemiology. I mean, there are more expensive portable devices that are a lot better for epidemiology. There are various devices with pumps and filters and things like that. I'm not going to name names. EPA always makes me say that on all of my papers for EPA-sponsored grants. But no, not endorsing anything, but for epidemiology, I don't think they're good enough. And for really telling, as Kelley said, they can miss a lot of traffic-related particles. They're qualitatively useful, but they're not quantitatively useful. And so over time, that may get, I don't think simple light scattering devices are going to get that much better, because I think it's inherent to the device. But over time, we may be able to develop shrunk technology that can produce better monitors that are more affordable and more widely disseminable.
Excellent. So another technology that came up, of course, was satellite observations. And Dr. Schwartz, you spoke at length about how satellite data can be used with other data sets to improve model predictions. So we know that satellite observations are continuing to play an ever-increasing role in how we understand atmospheric pollution. Are there specific outstanding research questions that you look forward to being addressed with satellite data, either current satellite products that are being disseminated or emerging ones over the next with missions that are upcoming?
Sure. So things went by pretty fast, but you may have noticed that the OMI NO2 was a significant was an important predictor in at least one of the models for PM 2.5, and I think that has to do with, its role in SOA formation, capturing some additional things that CMAQ wasn't able to pick up, right? Sentinel-5 has much finer resolution NO2 data. I mean, OMI is like 13 by 24 kilometers. NO2, varies from street to street. So Sentinel-5 won't do that either, but it's much finer resolution. And I think going forward, that's going to be useful. It's also, it measures formaldehyde and some other VOCs, and so it may be useful as well, where we may not have good enough emissions inventories for VOCs. We're getting some physical measurements that may be important. The new GOES satellites, they only have a 4-kilometer resolution, but it's every 5 minutes, and that means that the number of days in which there's no measurement is going to be a lot smaller, and that's going to make AOD measurements much more valuable. Of course, it's going to make the size of the servers that I need to buy a lot bigger also.
Much more valuable, yeah.
So it's going to be a computational challenge, but that's certainly going to help. And again, I think finer resolution, more monitoring of precursors is going to be, now we have satellite measurements of methane. Now, that doesn't matter so much for PM 2.5, but for ozone, that does matter, and so I think in general, satellite measurements are getting more accurate and more spatially and temporally resolved, and that's going to help.
Thank you. Dr. Barsanti?
I don't have a whole lot to add. I mean, I think about it in terms of that, like all measurements sort of have their blind spots, right? And I think about like what we can learn from like a long time series data. So for example, like the speciate network, right? Or these are the improved network is what I'm thinking about, right? So we have these networks, right, that are not that complex in the species that they measure, but it's like these really long time series of data with pretty good spatial coverage if you link these networks versus these field campaigns, right, where we collect a lot of different types of measurements in one location. And, both of these together really help provide a better picture. And I think when you add higher temporal and spatial resolution satellite information there, I think that, we just continue. I always think of it as better opportunities to constrain the models, right? To constrain and test, like better input, better output. And I don't think that we can overdo it, right? And even on a really local level, we found this with measuring the emissions from fires is that, the more instruments, every instrument has its blind spots. And so the more instruments you throw at a given problem, we really start to see a complete data set. So I viewed the satellite products in sort of that same lens.
Excellent. So we are over time, I believe. And so I will throw it to Havala. Would you like to send us off?
I'd like to thank both of our speakers, Dr. Schwartz and Dr. Barsanti, for their really insightful presentations and for answering the questions and the additional discussion. And also my co-host, Dr. Murphy and UNC for providing this conference forum for us. Thank you all.
Thanks, everyone.
Thank you so much.
And we'll hopefully see you next year.
Yeah, yeah, in person, right?
All right.